In this lesson, we will discuss the logic rules that we will use to prove mathematical statements. Previously, we discussed the axiomatic method, which is a method for proving that results are correct, and the requirements for an axiomatic system. The second requirement was a list of rules which tell us how and when one statement follows logically from another. We never gave the list of rules, and so that's what we're going to do in this lesson. The first ground rule, logic rule 0, says that no unstated assumptions may be used in a proof. So this logic rule goes along with the very idea of axioms, where we need to lay out all of our basic assumptions so we're very clear about the situation we find ourselves in when we're trying to write a proof. So it's very important not to leave out any assumptions that we think are obvious to the reader. We need to be very precise with our assumptions. So in all of mathematics, we are trying to prove theorems, and theorems are mathematical statements that are valid and hold under the given assumptions. When we think of mathematical theorems, we can write all math theorems as a conditional statement. That's an if-then statement. So we have a if, then some hypothesis, then a conclusion. Sometimes theorems are written kind of informally as just one conclusion, but we can always write theorems in this form, if H, then C. So a conditional statement says that the hypothesis implies the other statement called the conclusion. Symbolically, we let capital letters stand for statements. So H is the hypothesis statement, C is the conclusion statement. So we write if H then C as this notation, H with an arrow pointing towards C. So this is often read H implies C, or H if H then C. So our job as mathematicians is to write proofs of mathematical theorems. A proof is a list of statements together with justification for each statement, ending with the desired conclusion. So in a given mathematical system, the only statements that we will call theorems are those which have a proof. So a theorem is a statement that has a proof. And mathematicians use other words to describe these mathematical truths. Proposition is often used interchangeably with the word theorem. A corollary is usually an immediate consequence of a theorem. So you might prove a general theorem, and then as a consequence that has a very short proof, we call that a corollary. And then sometimes authors will use the word lemma, which is often used for a helping theorem. So you might want to prove a little lemma, which then makes a proof of another theorem simpler. So these are all names for the same type of mathematical statements. It just indicates how the author is going to use those in its presentation. So our next logic rule, logic rule 1, describes the different types of justifications that are allowed in proofs. Now the author, when he presents a proof, will often give several statements and puts a number before each sentence, each statement in the proof. And then oftentimes he'll give a justification in parentheses after a given statement. So these are the type of justifications that you can use when making statements in your proofs. By hypothesis. So we assume the hypothesis, and so then that gives us often one of the first lines in your proof. We assumed axioms, so we can say by axiom. We can always use a previously proven theorem, so we can use the logical consequence of a theorem by saying by theorem such and such that was proven previously. Oftentimes it might be a homework problem or an example in class or any other theorem. So previous results can be used as justifications in a proof. We can always use the definition as a justification. If we have a step in a proof that's already been proven, then we can use that previous step in our argument. So say by step 2 or by step 3, and you recall back to a previous line in the proof. And then we're going to have a total of 11 logic rules in this section. So we could say by some rule of logic. you should be able to justify each statement in your proof. So when we get more comfortable with proofs, they become less formal and they become more like paragraphs, more like essays, really. And the justifications are often omitted if they're obvious or if there's something that's a technique that's used over and over again. But again, we should never just leave out details of a proof and say, well, it's obvious, such and such. This can be very frustrating to the reader, and often professors get away with that, and a careful student will call a professor out on it and ask them to prove these obvious statements. Now, there are many techniques for proving theorems and proving statements, so we're going through the different rules that we would use to prove statements. It'd be nice to have just a clear-cut standard procedure, a rote method for proving or disproving every statement in mathematics. But it's actually been proven that no such rote method exists. This is a deep theorem in mathematical logic. So recently, this introduction of AI in modern society is given this idea of computers taking over everything. There's no way to prove every statement in mathematics using a certain method. It gives us hope that a computer will never put all mathematicians out of business. And writing proofs certainly comes more naturally. The more you do it, the more experience you have, the more types of proofs you read can help a student to write their proofs. But simple things that we can do to help us start our proofs is make sure you clearly understand the meaning of every term that's listed in the theorem. Look back at other theorems that relate to these topics or these definitions. Remind yourself of what you're trying to prove. Sometimes it can be helpful to start at the end of a proof and the conclusion that you want and actually work backwards. And then sometimes with geometric proofs, drawing a picture might help. So these are some tips you can use to help you start your proofs. Next, we'll talk about the most common type of proof that we'll see in this textbook. This is called a proof by reductio ad absurdum, which will abbreviate RAA. In a RAA proof, which the RAA means reduction to the absurd, we want to prove a theorem. So we assume we'll start with a theorem of the form H implies C. And we're going to start by assuming the negation of C. This contrary assumption is called the RAA hypothesis. So we're distinguishing that from just the hypothesis H. So we're going to make this temporary assumption that C is not valid. So we take the negation of C, and then through logical arguments, we'll see how that RAA hypothesis will lead to an absurd statement. So we need to show that the negation of C leads to an absurdity. So an absurdity is a statement that's clearly not valid, something that might contradict a known theorem or one of our foundational axioms. So if our assumption that the negation of C was valid leads to an absurdity, then we could conclude that C actually must be valid. And so that's our RAA conclusion. So you may have used a proof by contradiction in a previous class or in looking at proof techniques. Proof by contradiction is an example of an RAA proof where we assume the contrary to the hypothesis C and then get a contradiction, which is the same thing as absurd statement. So to summarize, we're going to call this logic rule 2, RAA proof. So to prove H implies C, start by assuming the negation of C and deduce an absurd statement. And then to do that, we need to use the hypothesis H if necessary in your deduction. Once we get an absurd statement, then it follows that C must be valid. One of the classic examples of a reductio ad absurdum proof was found thousands of years ago by the Pythagoreans, and in their proof that the square root of 2 is irrational. So to prove that square root of 2 is irrational, we're going to first make our RAA hypothesis. That is, that suppose that the square root of 2 is rational. And we haven't officially defined rational, but we know that rational means that you can write square root of 2 as the fraction of two integers, p and q. I can say further that q is not equal to 0. But we have square root of 2 written as a fraction of integers. And moreover, we can assume that this fraction, p over q, is actually a reduced fraction. That is, so if p and q had any common factors, we could cancel them. So, for example, if you had a fraction like 4/6, you would cancel a common factor of 2 and get 2/3. So we want to assume that we have a reduced fraction. This is an important assumption. In other words, p and q have no factors in common. Then we can, just through using the rules of algebra, we can clear the denominator, and we get root 2 times q is equal to p. Then we'll square both sides of this equation, and we'll end up with 2 times q squared equals p squared. Now, if we look at the left-hand side, we have an integer multiple of 2. So the right side, which is p squared, must be an even number, just by definition of even. And since p squared is an even number, and we know that p is an integer, it must be true that p is even, because we know that the square of an odd number is odd. So we can conclude that p is even, and we can use the definition of even again and write p as 2 times some other integer r. Now I'm going to substitute this in the previous equation. We had 2q squared equals p squared, so if I substitute a 2r in for p, I get 2r the quantity squared, which is 4r squared. And now if we start on the left, we have 2q squared equals 4r squared. There's a common factor of 2 on both sides of this equation. So I can cancel 2 from both sides, and I get the reduced equation q squared equals 2r squared. But using the same reasoning as we did earlier, we see that the right-hand side of this equation is an even integer, so q squared is even, and we conclude that q must be even too. But there's an absurd statement, because we said that p and q have no common factors, but we just concluded that p must be even and q must be even too, so they would have a common factor of 2. So this is an absurdity, and we can make our RAA conclusion that the square root of 2 is actually irrational. Now let's talk about some notation. We're going to, again, let capital letters stand for statements. So let's let S and R be statements. We'll need to talk about the negation of statements. So the negation, or contrary of S, it's denoted by a tilde in front of the S. So this like squiggly line in front of the S is a tilde. That means the negation of S. Oftentimes it's read not S. Mathematical statements often use a conjunction using the word and. So the symbol S with an ampersand and R, that is called a conjunction, and it stands for S and R. So both of those statements, S and R, are valid, then S and R is valid. Our author uses the ampersand sign, so I'm going to be consistent with the textbook, but in other mathematical textbooks, the and symbol looks like a caret, like the upside down V. This is another way to write S and R. And you can use it interchangeably. I think this is easier to write than an ampersand, personally, by hand. But I'll type it up as S ampersand R for the conjunction. The disjunction, S or R, means this is the mathematical statement that is equivalent to saying that S is valid or R is valid or both are valid. So we don't, in everyday English, we kind of mean an either or, like would you like one or the other, but the mathematical use of or is always one or the other or both. This is often written as S with a or symbol and an R. It looks like a little V in between the two statements. But again, I'm going to use the author's notation where he actually writes the word or for the disjunction. A contradiction is one of these absurd statements that we're trying to get when we do these proofs. A contradiction is a statement of the form S and not S. So we assume that a statement can only have one of two values, means valid or not valid. So assuming the statement S and not S would be a statement that is always false. And so this is called a contradiction. The next rule is logic rule 3, which is the statement that the negation of S means the same as S. So whenever you negate a negative statement, you get the original statement S. Now in the RAA proof method, we had to negate an implication. So we need the next rule. Logic rule 4 says that the negation of H implies C means the same as H and not C. So we think of this as if it's not valid that H implies C, then that must mean that there is a case where H is valid, but C is not valid. So that's why the negation of H implies C is equivalent to H and not C. So for an example, if I wanted to write the negation of if X is prime, then X is odd, I would write that as negation as X is prime and X is even. The next rule tells us how to negate a conjunction. Since conjunctions occur so often in our mathematical statements, statements like S and R, if I wanted to take the negation of S and R, that means the same as the negation of S or the negation of R. So we know that the negation of an and statement is an or statement. So for example, the negation of the statement the natural number X is odd and prime would be the natural number X is even or composite. Most mathematical statements involve variables, and so variables can be quantified in two different ways. The first way is the universal quantifier, and so we see these kind of phrases in statements, mathematical statements and theorems, for any X, or for every X, or for all X, or given any X. And so the universal quantifier is upside down capital A. So when we see this symbol upside down capital A, X, that stands for these statements. And from the context, we know how to read this. This can be interpreted as for any X, or for every X, or given any X. And if we have a statement about the variable X, let's call it S of X. So S of X would be read statement S about X. We can use this universal quantifier in front. And so we'd say for every X, S of X. And so this is a common way for using these quantifier symbols to shorten our notation for mathematical theorems. The other way that we quantify variables is the existential quantifier. These are statements that start with for some X, or there exists an X, there is an X, or there are an X, there are X such and such. And the existential quantifier is the backwards capital E. So when we see this symbol, backwards capital E, X, we can be interpreted as the statements similar to the ones above. For some X, or there exists an X, there is an X, and so on. And the same we did with universal quantifier. We can use this in mathematical statements about X. We would say something like, for some X, S of X. For some X, statement S about X. This next rule, logic rule 6, tells us how to negate a statement that has a universal quantifier. So if we're denying that a statement S of X holds for all X, that's the same as saying that for some X, statement S does not hold. So logic rule 6 says the statement that the negation of a for all X, S of X statement means the same as there exists an X, negation of S of X. So there exists an X such that not S of X is valid. Similarly, for the negation of an existential quantified statement, this rule, logic rule 7 says that the negation of there exists X, S of X means the same as for all X, the negation of S of X. So to deny that there exists an x having some property s of x is to say that all x fail to have property s of x. So let's look at some examples of negating quantified statements. Euclid's fourth postulate states that all right angles are congruent. So this is a universally quantified statement. So the negation of this universally quantified statement will be an existential statement. The negation would be that some right angles are not congruent. Let's look at an example using real numbers. Let's assume we have x and y real numbers, and let's look at a statement that has two quantifiers. So the statement, for every x there exists a y such that x plus y equals 0. This is basically a statement about every real number having an additive inverse. So that would be kind of the more normal English way of saying this. Every real number has a additive inverse. So for every x there exists a y such that x plus y equals 0. So we know this is a valid statement, but nevertheless let's negate this so we see how to deal with two quantifiers. Well, each quantifier would have to be switched. So if we take the negation of the statement, the first quantifier for all x would become there exists an x, and then as we negate the next quantifier, we get for all y, and then we would take the negation of the statement x plus y equals 0. So finally we would get the statement there exists x such that for every y, x plus y does not equal 0. So that would be the negation of the original statement. So this statement that we started with is explicitly written using quantifiers, but oftentimes this is not the way theorems are presented. They're usually written in a more informal way, like all real numbers have an additive inverse. So it's oftentimes necessary to translate a given theorem or given statement into a more formal setting before we can negate them. So oftentimes the way a theorem is written, it actually hides the quantifiers. So it can be helpful to rephrase a statement before trying to negate it. So for example, the statement, if a line intersects one of two parallel lines, then it also intersects the other. This mathematical statement hides some quantifiers about all parallel lines. So in order to negate this, I would like to rephrase this so I don't hide the quantifiers. So this is a statement about all pairs of parallel lines. So I'm going to start by quantifying this for every pair of parallel lines, and then I'm going to write the statement as a conditional statement, if then. If a line intersects one, then it intersects the other. So now we have a nice form that we can negate. We know how to negate the for every statement, and we know how to take the negation of if-then statements. If P then Q, the negation would be P and not Q. So let's look at the negation. There exists a pair of parallel lines, so that's the negation of for every pair of parallel lines. And then the negation of the if-then statement, such that a line intersects one of them and does not intersect the other. So there exists a pair of parallel lines such that a line intersects one of them and does not intersect the other. Let's look at another example of hidden quantifiers. Consider the statement, every even number larger than 2 can be written as a sum of 2 primes. So just like I did in the last example, I want to first rephrase this by showing the hidden quantifiers and writing this as an if-then statement. So we're talking about every natural number x. So I'm putting a variable in so I can have a quantifier and make precise statements about equality. For every natural number x, if x is even and larger than 2, then there exists prime numbers y and z such that x equals y plus z. So see, we have an if-then statement. in the hypothesis of the if-then statement, we have a conjunction, x is even and x is larger than 2. Then in the conclusion, we have an existential statement. There exist prime numbers y and z. So when we negate this conclusion, we'll have to have a for all statement. So let's look at a negation. For every natural number x, the negation would be there exists a natural number x. And then we're going to do p and not q for our negation of the if-then statement above. There exists a natural number x such that x is even and larger than 2. That's the hypothesis p. And then we need a not q statement. So for all prime numbers y and z, x does not equal y plus z. The next rule is logic rule 8, which is known as modus ponens, or the rule of detachment. It's the following rule. If P implies Q and P are steps in a proof, then Q is a justifiable step. So this rule is used so often, it's pretty much the definition of what we mean by implication. We've shown that P implies Q, and so if we have the statement P being valid, then we can assume Q. When talking about these conditional statements, we often come across the converse of a conditional statement. So if we start with the statement P implies Q, its converse is the statement Q implies P. Now it's very important to note that these statements are not equivalent. A simple example is the statement, if an integer is a multiple of 6, then it is a multiple of 3. So this is a valid statement. But if we look at its converse, the statement, if an integer is a multiple of 3, then it is a multiple of 6, this is not a valid statement. Q implies P is not always true. It's not always a valid statement for a statement P implies Q. Now, it might happen that both the conditional statement P implies Q and its converse are both valid. When that happens, we have a biconditional statement. So if P implies Q and Q implies P are both valid, we write P if and only if Q. So the if and only if symbol is a double-sided arrow, which has the connotation of P implies Q and Q implies P. So we say P if and only if Q, or we could say that P is logically equivalent to Q. So we can always write definitions as a biconditional statement. They always have this form, P if and only if Q. Even though sometimes definitions are not written in that form, they can be written as biconditional statements. Another statement that we often come across in proving mathematical theorems is called the contrapositive. The contrapositive of P implies Q is the statement not Q implies not P. These statements are equivalent. Sometimes it might be easier to prove a contrapositive of a given statement. Back to our last example, if an integer is a multiple of 6, then it is a multiple of 3. The contrapositive would be, if an integer is not a multiple of 3, then it is not a multiple of 6. These statements are equivalent. The next rule gives a few more ways that implication is often used in proofs. Logic rule number 9 starts with P implies Q and Q implies R implies P implies R. Next, part B, if we have the validity of P and Q, then that implies P. And the third part of logic rule 9 is essentially saying that the contrapositive is logically equivalent to a implication P implies Q. So not Q implies not P is logically equivalent to P implies Q. So all of these statements are what we call tautologies. These statements are always true just by their form, and we don't have to worry about the validity of the individual statements, P, Q, and R. Logic rule number 10 is called the law of the excluded middle. It states that for every statement P, the statement P or not P is a valid step in a proof. So this characterizes the classical two-valued logic that says that either a statement holds or it does not. There's no middle ground, such as we don't know whether P or not P. So this is the basis for the idea of a proof by cases, which we'll see in logic rule number 11. So with logic rule 10, we can think of breaking a proof down into two cases where a statement P or statement not P are valid. But a proof by cases can have any number of finite number of cases. And logic rule 11 says that suppose you have statements S1 or S2 or S3 all the way up to Sn, and this is a valid step in a proof. So the idea is you've taken your proof and you've broken it up into cases. So you have n different statements. Now we're trying to conclude that C is valid. So let's suppose a proof of statement C is carried out for each one of the cases, S1, S2, all the way up to Sn. Once we've shown C in all possible cases, then we can conclude that C is a valid step in the proof. So this is the last logic rule that we're going to use, and we're not claiming that we've listed all possible logic rules, but these should be sufficient for our purposes in discussing the foundations of geometry.